Hello, my name is Tiffanie Edwards, and I will be presenting the paper on exploring the subdomain of artificial intelligence or AI model forensics. I worked on this paper with my research partner Syria McCullough and our two mentors Dr. Mohamed Nassar and Dr. Ibrahim Baggili. We all come from the University of New Haven. Syria and I are current graduate students completing degrees in cybersecurity and networks, and we are both a part of the university's research team, University of New Haven Cyber Forensics Research and Education Group, or UNHC-FREG for short. Dr. Nassar holds a master's degree and PhD in computer science. He specializes in the area of cybersecurity and machine learning research. He is also an assistant professor at the university. Dr. Baggili is the director of the Connecticut Institute of Technology, which resides at the University of New Haven. He also leads the UNHC-FREG team and specializes in all areas of digital forensic research. Before we begin, we'd like to acknowledge the NSF for funding this research project. We'd also like to say that our views do not necessarily reflect those of the organization. Today, we will be sharing our motivation for researching AI model forensics and sharing the contributions we made throughout this research project. We will also be going over three closely related areas of focus within digital forensics, providing a case study that deepened our need for further exploring this area, and discussing the challenges that will arise in this emerging field now and in the future. We will also close by sharing our future plans for this project. The contributions we accomplished in this paper are listed in this slide. To highlight a few, we described how the fields of software forensics, cloud forensics, and network forensics are related to AI model forensics. To further explain the usefulness of these fields, we examined a fictional case study and related hypotheses and investigative questions to each area of focus. Along with discussing the relation of those digital forensic fields to AI model forensics, we also discussed how AI model forensics will inherit challenges from the related fields. First, we'd like to go over the general steps of model generation and model deployment. Saved model files can be used for transfer learning, to train models over new datasets, packing distribution, hosting, or deployment. This figure depicts the simple and general steps of creating an AI model before deployment. Deploying or serving a model means to turn it into a usable model to host in a production environment. A model file will be needed for deployment because the files contain information about a model's architecture and parameters. For example, in deep learning models, the model file will contain information about the layers and weights, and in K-means clustering machine learning models, the file will hold information about the cluster centroids. The model file is the output of the first three steps of the pipeline in the image. The file is generated only once the creator determines that the performance of an AI model is sufficient, and the creator can generate as many model files as needed. In our paper, we defined AI model forensics as a subset of AI forensics that focuses on how to address AI model artifacts such as files, logs, model authenticity, classification history, and others, and how to promote the forensic soundness of these artifacts. We also acknowledged two major categories where AI model files might be integral to an investigation: AI as a tool crime and AI as a target crime. AI as a tool crime implies that systems or services are used to commit physical crimes or aid in cyber crimes. Previous research has been done where AI models are created and viewed as malicious by design, and the investigator set out to determine if and how an AI system caused a malicious incident and why the incident was caused in the first place. From that perspective, AI as a tool can become malicious by design through methods of tampering, and then the model is used as a malicious tool by a perpetrator. In contrast, AI as a target crime implies that vulnerabilities in AI-enabled systems are exploited or hijacked. Potential threats include, but are not limited to, manipulation of training data, malicious code change or replacement, and tricking AI systems into improper operation. With any forensic approach, the collected evidence should answer questions related to the when and where of the crime, who was the criminal, what was the crime's target, and how the crime occurred. Defining a forensic approach for model forensics will help investigators answer these key questions about AI systems, whether it falls under the category as AI as a tool crime or AI as a target crime. This figure depicts possible locations where forensic evidence pertaining to AI forensics is likely to reside, and it includes 3 other digital forensic areas that are likely to have a strong crossover with AI model forensics. As mentioned before, those 3 areas are software forensics, cloud forensics, and network forensics. The 4 principal applications of software forensics are author discrimination, author identification, author characterization, and author intent determination. All of these principles can help identify the author or creator of an AI model. Knowing the creator of an AI model can give investigators insight into whether or not an AI system was created with malicious intent or became malicious after its creation. The feasibility of software forensics has been questioned in previous research. Author identification may be subject to false positives due to insufficient amounts of data or recurring anti-forensic techniques, such as code reuse from other authors to increase the similarity to legitimate code. However, it has been shown that with a sufficient amount of data and a careful choice of appropriate and distinctive characteristics, software forensics proves useful in reverse engineering and authorship attribution. AI model forensics is strongly tied to cloud forensics because model files will be deployed in cloud environments. This means the memory forensics of that cloud server may hold forensic artifacts that relate to the file itself. The end-user systems that are actively utilizing an AI model may also hold forensic information either physically and locally on a host machine or on their server. Cloud data is described as fragile and volatile, which makes correct data extraction a very sensitive process. Remote data collection and preservation is more difficult than its standardized counterpart for collecting physical evidence at a crime scene. Network forensics involves evidence that can be seized from within the network and outside of the network. Evidence within a network includes device logs, network traffic, and the volatile memory from the devices in question. Evidence processed from outside the network can include Internet archives and logs from the domain hosting provider, domain name controller, and Internet service providers. Because AI models will be deployed in the cloud service provider's network may hold digital forensic evidence that may be relevant to a case. The network of end users using an AI model may also hold digital artifacts, which we mentioned may also be the case in cloud forensics. The future direction of network forensics corresponds to the rise of cloud-based applications and the importance of cloud forensics. Past researchers of network forensics recommend that instead of only using packet capture files of network segments for analysis, investigations need to include packet capturing and analysis in cloud environments. To better understand the context of AI model forensics, we present a case study where an AI-based model decides on surgery based on patient information. This is described as an autonomous need for surgery classifier. Examples of patient information that are taken into consideration when the AI system is determining the need for surgery are patient age, life quality, current and previous symptoms, past medical records, and more. In this scenario, the system decides what action should be taken by a surgeon, whether it is microsurgery, radiosurgery, or just active observation. The system was previously helping medical staff make good decisions when suddenly the system started outputting bad decisions, which led to the confusion of medical staff and the occurrence of several deaths. This called for an investigation. In our case of this investigation, the investor came up with the hypotheses of what could have gone wrong with the system. Those hypotheses, which are also written on the slide, are: the model has been completely replaced, the model has been gradually modified and poisoned, the model was always malicious, but the malicious aspects remain dormant, the problem occurred after an update of the libraries or some dependencies, a problem in feature extraction and pre-processing occurred following a recent code pull, the addition of new features to the model decreased its accuracy. As you can see from the slides, the first 3 hypotheses are indicating malicious intent, either from an outside perpetrator or the creator of the model. The last 3 hypotheses have reasonings that are benign, but still resulted in a faulty AI system that caused deaths. An investigator will want to answer some of these questions on the slide when conducting their investigation. Those questions are: where is the model hosted? Is it locally in the internal network or deployed as a web service on a cloud platform? What is the access control policy? Who has access to the model and who has access to the hosting system if there is one? In the case of cloud deployment, what is the service model? Is it platform as a service, software as a service, or infrastructure as a service? Is the hosting system properly protected, patched, and updated? If the model is deployed from the local system, forensic evidence about the model may reside in memory. If the model is served and deployed from the cloud, most of the evidence resides in the cloud. However, some residual evidence may also reside on the end-user machine, which we discussed earlier. The more important questions our investigator will face are determining the original intent of the model, who made the modification, was the modification authorized, what exactly was the modification, and to what degree did it alter the model's intent. Software forensic methods and techniques such as author identification, characterization, and intent may help the investigator find some of those answers. Some other investigative techniques include malware checking whether the host was infected by any kind of malware or was the target of offensive black hat penetration testing. Using adversarial samples, the investigator may want to test the sensitivity of the model to adversarial samples generated by well-known algorithms. If the model is vulnerable to these samples, the investigator may test logged input vectors to check if they are adversarial as well. Visualization techniques may also help. Those techniques such as T-distributed stochastic neighbor embedding and uniform manifold approximation and projection may help determine whether the classifier is a poor one or whether the input data is noisy and inconsistent. And lastly, the investigator may want to employ well-known explainable AI techniques to generate explanations for the inquiry decisions. The explanations can be checked by experts to see if they make sense or not. Good explainers tell a lot about possible model overfitting, underfitting, or adversarial behavior. In the case of the explanations are incoherent with human expert reasoning, given the input features, the investigator has to turn back to earlier parts in the AI pipeline, such as data input and feature extraction. The AI model forensic case study can also be used as the justification for creating AI model ballistics. The goal of AI model ballistics is to identify important information for an investigation such as the one described. The information would include aspects such as the type and creator of a model, the intention of the model, the compliance of the model with the creator's original intention, the framework, tools, and datasets used in creation, and any other information that is deemed important enough to help this investigation. For this reason, we believe AI model ballistics is defined as a subfield of AI model forensics, and it will help answer the aforementioned questions and investigations pertaining to the AI model artifacts that are left behind on systems or servers. Moving on to the challenges, we believe AI model forensics will inherit all of the challenges of software, cloud, and network forensics and more as it develops in the future. In cloud forensics, the evidence cannot be physically collected and the data can be dispersed throughout numerous servers and architectures. The AI model service may be dependent on other web microservices or federated learning. This makes it hard to physically acquire and seize evidence for an investigation. Investigations will need to rely on help from cloud service providers, which makes the chain of custody and the validity of the evidence less credible. It also makes legal and jurisdictional challenges more pressing. Also related to legal and jurisdictional issues, AI models are usually generated by AI code that links to different developers, researchers, and providers. AI models are also typically located in shared storage and use shared computational resources. User privacy in these settings is an additional challenge. It is difficult investigating one user's data without accessing and violating the privacy of other users. Applying methods of software forensics may not be directly applicable to AI models and source code, which we mentioned before. Also, the swift development in AI frameworks and deployment models make the investigative search space even larger, and it just continues to grow. Lastly, as always, anti-forensics measures and adversarial attacks are always a concern in any area of digital forensics. We wanted to show the data we collected throughout our research about the current AI platforms, tools, frameworks, and deployment providers. As you can see, there are quite a number of available resources in each category. This is what we were referring to when we said the investigative search space is very large and continuing to grow. At the conclusion of this research project, we decided to continue further exploring AI model forensics and begin to develop techniques and methods that can be used in real investigations. To accomplish this, we plan to apply and create scenarios to develop a sound methodology for AI model forensics in end-to-end investigative use cases and explore any produced artifacts. We also plan to focus more on applying software forensic techniques by exploring in depth the contents of a model file. Hopefully, we will gain more insight about how the challenges of software forensics will affect AI model forensics in the future. Thank you all for listening to the presentation. If you'd like any more information about this project, feel free to contact any of the emails on this slide at any time. Thank you.